Hello there, welcome back to another video for today. Again, full ball pen and full explanation must be written down in order for you guys to improve. The first question about state the y distance is a scalar but displacement is a vector. Okay, now this is because distance only has magnitude, okay, and displacement has both magnitude and direction. Okay, all right. So you need to make sure that you're saying that it is the distance. Distance only has magnitude, that's all. But displacement, it can have magnitude and direction. Direction is the most important one, and direction. Yeah. Now this one here, you'll have to measure the distance is walked. Now you're going to use a ruler. You're going to measure this distance here from X all the way through the path. So this is the distance, how much ground they've actually covered. Okay. Now there's a range for this, and the range would be any range. I would say the range that we are going to accept would be 950 all the way to 1200 meters. Again, so it says here scale, and you know it has to be meters. Now for those of you turning in kilometers, that is also acceptable, but this here is the range. You need to use a ruler, measure this properly. Okay. Alright, so this is the range. Now the next one, you'll have to measure the displacement. Now displacement is pretty much where you were. Okay, you were at X, and then you just went straight to Y. So this here is your displacement. Okay, so where you were and where you end up in a straight line. So that is displacement. So all you do is you have to measure from X straight to Y, and this is roughly between 350 to 420 meters. Okay, now the important part. Displacement is a vector. Now vector must have a direction, so therefore we need to add the direction there. So therefore the direction for this one is where? It is north. So therefore we need to say our number and then north. Okay, for us to get, so this is one mark and this is one mark with direction, and this is just one mark there. Okay, now here we go. Now describe the motion. First of all, what graph it is? It's the velocity time graph. So y-axis has velocity. Okay. Now describe the motion between A. So A and B. Now A and B, we can see the line is flat. If the line is flat, it means that the velocity is staying at 20. So look, staying at 20, 20, 20, 20. So therefore, what it means, the line is flat, is staying at 20. So therefore, this here is a constant. Constant velocity. So velocity stays the same. Okay. Now move on. Now acceleration. How can we get acceleration? Now, acceleration is the gradient of the line. Okay, so therefore it's going to be change in y over change in x. Now you can also use the equation for acceleration, which is final velocity take away initial velocity divided by time. So this will also work. So let's have a look. So between B and C. So B is here and C is here. Now what is the final velocity? The final velocity is -7. So look, so here -7. So therefore -7 minus, what's the initial velocity? Initial velocity is B. So B is 20. So therefore it's going to be 20. Okay, whole thing divided by time. So how long it took? So it goes from 15 to 20. Okay, so how long is that? So this is 5 seconds. So therefore this is 5 seconds. So therefore the answer is going to be, the acceleration is going to be minus 5.4 in this case. Okay, 5.4. All right. Now, why is it minus? Is because we're looking for acceleration. Okay. Now, if the question asks us for deceleration, okay, then we can say deceleration is 5.4. But the question wants us to find acceleration, so therefore we need to put a negative there. Okay. Why negative? Because the formula is giving us negative, and also look at the line. The line is going down. So from B to C, it is decelerating, going down. Okay, so therefore this is the answer. Now if you need to, the question is asking for the units, but we need to put the units there to be correct, m slash s squared. Okay, meters per second squared. Good. Now the distance. Now look, the question asks us for the distance. The distance is going to be the area on the graph. Okay. Now let's take what we got. First of all, I'm going to delete these annotation to make our life much easier. Okay. Good. Now what we have is we have this shape here. Let's take a look. We got one. This shape here. So I'll call this shape A. I have a small triangle here. We'll call this 2. Okay. Now here I have a little shape here. Let's call this 3. And then I have a small triangle here. Let me call this 4. Okay. Now first of all, distance is a scalar. So therefore we don't need direction. So okay. Now velocity is a vector. Okay, so the negative here is telling us the direction. So the negative here is telling us the direction. -7 is going the other way. Okay, so we don't need this. So therefore, no need for minus. Okay, we don't need minus. All right. Now let's take a look. So it will be the area A plus 2 plus 3 plus 4. Yeah, so we've got 4 areas, isn't it? So 1, 2, 3, 4. Okay, now let's do one by one. So let me zoom in. Let's do one by one. So area 1, let's do this here. So area 1 is going to be half times A plus B times height. Okay, now let's take a look. So half says half. Bracket, what's A and B? A and B is the parallel line. Now if you're going to do it like this, you can easily break it down into smaller chunks. You can break it down into the small triangles and rectangle. Yeah, you can do that. Okay, so A and B. So A and B is going to be, so from here to here, so this is 10, and here to here, this is 15. Okay, so therefore it's going to be 10 plus 15, and then the height is 20. Okay, this will give us 250 meters. Now we need to do number 2 again. So number 2 is a triangle. So half times base times height. So half, you can see that I'm adding all the working out, because that's what the question wants, the working out. Yeah. Okay. So half. Okay, base. Now what's the base for this one? So from 15 to 18, that is 3. Okay, so base times height is 20. Okay, so that's 30 meters. Okay, now let's do number 3. Number 3 is another there. So A plus B bracket height. So half is the half. Now let's take a look at A and B. Now here we go. Now A. So let's do A from here. Yeah. So let's go from 18 to 23. So this is 5. From 20 to 3, that is 3. Okay, so 5 plus 3 times. Now the height, look at the height. The height is this one here. So from 0 to -7. The negative is for direction. The negative is for vector. So we just need scalar. So therefore it's going to be, let me just write this in red. So this is going to be 7. Okay, we don't need the negative because we're dealing distance, and distance is a scalar. We don't need the direction. Okay, and this will be 28, and then number 4, which is the triangle at half times base times height. So half is half. Base, what's the base of the last triangle? The base is from 23 to 27, that's 4. And okay, so 4, and then the height is also 7. Okay, 7. Here we go. So 14 centimeters and 14. Okay, and now the air. What is the area? So area, you just add them together. So 250 plus 30 plus 28 plus 14. Okay, so let's add this up together. this will give us 322 meters. Here we go. And this is the wall working out. Okay, so here we go. So for those of you who got this wrong, we need to see all the working out. So again, see 1, 2, 3, 4, and then you add them together, and so on and so forth. Good. Now, what is the equation linking these things together? So this is F is equal to ma. Okay. Now here we need to find the acceleration. So therefore, let's do F is equal to ma. So let's rearrange this. So A is equal to F over m. Now F is the resultant force. So we need to find the resultant force here. So let's simplify this. So therefore, so look, this here and this here are the same, so they cancel out. So therefore, we're left with 20, and then 10, and then we can simplify this again. So therefore, we're going to have the object moving to the right at 10 newton. So therefore, it's going to be 10 divided by 50. Okay, and then we get 0.2, and we need the units for this one, meter per second squared. So the units is very important in this case. Okay, because we were looking for the acceleration. So earlier here we were calculating from the gradient, so that was fine, but here we need to find what is it. Next question is about energy. Now calculate the gravitational potential energy. So this one you guys should know this. So GPE is equal to mgh. Now m is the mass, we know is 50. G we know, now G is given to us here, so we need to use what the value is given us times 20, and this will give us 9,800. So this is the gravitational potential energy. Okay, so this is how much it got at when it jumped to the point here. So at this point, that's where you got this much energy. Okay, now let's keep going. Now 80% of this energy has been transferred into the kinetic energy. So here it's telling us not all energy has been transferred to kinetic energy. Okay, so normally, so GPE is transferred into kinetic energy, but here that is not the case. So here only 80% of that. So therefore, what we need to do is we need to do 80% of, and this will give us 7, 8, 4. So 7, 8, 4, 0. So this is the energy. Okay. So therefore, what's going to happen is as it's falling, that's how much energy it's going to have. Okay. So now, when we calculate this energy here, when we calculate the speed, what we need to do is kinetic energy is equal to half v squared, and then this is the energy that we need to use, because that's how we know. So we know that after falling 8 to 20 meters, 80% of it is converted. So therefore 80% is this one here. So therefore we need to rearrange this first. So half, so the half here goes on the other side, becomes 2. Okay, m v squared. Okay, so times 2. The m we divide by m v squared, and then this times 2 divided by m, and the whole thing must be square root, and then we get v. So therefore this is equal to times 2 divided the mass, and the mass you know is 50, and the whole thing square root, and the answer we should get is roughly about 18. Okay, roughly about 18 in this case. Okay, now the question says 2SF, so therefore you need to write your answer in 2SF. Okay, so 18 in this case. Okay, now here the ball is rolling along the ground, it slows down, so it slows down and eventually comes to stop. So it's rolling along the ground. So here's the ground, okay, so it's rolling around on the ground, and then it comes to a stop. Now what happened is, since it's rolling, it's going to have kinetic energy, so therefore kinetic energy, okay, is transferred. Again, the word that we need to see is transferred, because the question says describe, yeah? So we need to write the word transferred. Okay, now if you draw a diagram, okay, then if you diagram, so if you put the arrows, you need to put transfer on top of the arrows. Otherwise, this will not count. Why would it not count it? Because the question tells us to describe. Okay. Now, if the questions tell us to draw, then you transfer that. That's fine. But here the question tells us to describe. So therefore, we need to describe in words. Okay. So energy is transferred. Okay. To thermal energy. Okay. To thermal energy. All right. And thermal energy is pretty much to the surrounding, so to the surrounding or to the ground. So put bracket here. So surrounding slash ground. Okay. So how is this doing this? So this is doing via mechanically. Oops, misspell this there. Mechanically. Again, so we need to see those words. Remember, the keyword is transfer. Kinetic energy to thermal. Why kinetic energy? Because it's rolling. Okay. Thermal, because that's how it gets stopped. Okay. And here we go, mechanically, because friction. Yeah, because friction is going to mechanically stop it. Right, now next one is a 6-marker one. So this is a very, very good question. Okay, now let's take a look what we got. Okay, now after knocking down the wall, so it's already knocked down the wall, and then the ball is allowed to swing freely. Okay, now the graph shows how the height varies with time. So the height, so after hit the wall, it's gonna swing, and the swing gets smaller and smaller and smaller and smaller. You're going to get smaller, smaller, smaller. Describe, explain how the energy changes during this time. So this time is after it's been knocked out. Okay, the swing consists of swinging the balls and surrounding. Okay, now first of all, we need to identify that this is indeed the case. What we're going to do is we're going to draw a diagram. So after is knocked down, so therefore, let me go back to the diagram. Okay, so knock the diagram, so it's going to be something like this. So let me call it A. Okay, so it's going to go to B, going to go to C. Oops. Can I go back? Let me just delete this. Yeah, I can delete this. Okay. Go C. And then what's going to happen is the swing is going to get weaker and weaker. And then the swing, okay, so we got B here. Go to C. It's going to get smaller. Back to A. It's going to get smaller. So this, see, the extreme gets smaller and smaller. Okay, why is that? Now, first of all, we're going to start. So what I'm going to say at A. Let me zoom in so you can see, because we need to get these full marks. Yeah. So what happened is at A, that's one. So at A, it's going to have maximum gravitational potential energy. It's going to have maximum gravitational potential energy at A. So at A, it's going to have maximum, and even at C, it's going to have maximum. Let me just write it there. At A, that's fine. Let me just start from one, and then we go through to the next one. Yeah. Okay. So maximum kinetic, maximum gravitational potential energy at A, and then it's going to have 0 kinetic energy at A. Okay. Now what's going to happen is from A to B. Right. So GPE is transferred to kinetic energy. The GPE is transferred to kinetic energy. How is that transferred? Mechanically. Okay. It's transferred mechanically. All right. Now, at B, what's going to happen at B? So at B, it's going to have maximum kinetic energy and minimum or 0. Ooh, let's have a look. Okay, let's say 0. Okay, this is 0. Okay, that's a 0 GPE. Because it's still suspended in the air. You know what? Let me just change the word here from 0 to minimum. me change the 0 to minimum. Okay, so it's going to have minimum was 0. So even if we say 0, it should be fine. Okay, so maximum kinetic energy, minimum energy. Okay, so why does it have maximum kinetic energy? Because it is moving the fastest, at the point. Okay, so anything swing the fastest at B. Okay, swing the fastest at B. Right, and then from B to C, what's going to happen from B to C? So the kinetic energy is transferred to GPE, again mechanically as well. Mechanically, yeah, mechanically. It's changing mechanically. Alright. So what we've done here, okay, so we've done maximum GPE at A and minimum blah blah, blah and so on and so forth. Alright, now what we're going to add is going to add a little bit of more details. What's going to happen, yeah? So maximum GPE at A, okay, because okay, it is at the highest point because at highest point. Okay, and same thing here. Okay, so graph to GPE, so to uh, mechanically, okay, mechanically, and then at C, it's going to have so kinetic energy, so it's going to have max GPE and minimum or 0 kinetic energy. Okay, again because it is at its highest point. Okay, now we have from A to B to C. Now the question that we want to ask ourselves is why does it get smaller and smaller and smaller? So why does it get smaller and smaller and smaller? Okay, right? Why does it get smaller and smaller and smaller? Now this is because, all right, this is because energy is lost or energy is dissipated. Energy is dissipated slash lost to surrounding. How is it lost by surroundings? Because of air resistance, yeah, because it is swinging in the air, so therefore there's air resistance, and air resistance is going to cause the energy to be lost in this case. Okay, and what's going to happen is this, okay, this reduces the kinetic energy and the GPE. Okay, thus, okay, decreasing. Okay, let me take a look what's happening. Decreasing the height of the swing, decreasing the height of swings. Okay, so here we go. Now 6 marks, 1, 2, 3, 4, 5, 6 points. Okay. Okay, here we go. Again, so if you got this wrong, make sure that we do have everything fully properly done. Okay, and if there's something that we did not understand, so hopefully now we know what we need to do. Okay, now next one, let's move to the next one. So this is the principle of energy, sorry, principle of moments. Now this one should be straightforward. Okay, so object in equilibrium, so so for the object in equilibrium, so what happened is the total anti-clockwise moment is equal to total anti-clockwise moment. Alright, now 2 marks, you need to say the first one and you need to say the second one properly to get the second full mark. Now moments, you need to remember the equation for moment is equal to force times perpendicular distance. Now the force we know is 280. Now, so this here must be converted. Okay, so 90 must be converted. You divide by 100 to convert this to meters. Now, how do I know if it had to be meters? You guys learned this before, but also the unit says Newton meter. Okay, so therefore the answer is 252 meters. Good. All right. Now here we need to work out. So the drummer pushes with force F. So this force F we know. So this is 1.5, and we're looking for this here. Okay. Now what I'll do is I'll redraw this in terms of the nice lever and pivot. So we've got the pivot here. Now what we have is this is the pivot. Now, we want to identify which ones are anti-clockwise and which are clockwise. Now, this force here goes down, yeah? Now, if you allow this force to rotate fully, so this force here, rotate fully, that's going to be like this. Rotate all the way up. So this is anti-clockwise, so therefore I'm going to put this force here. So this is 1.5 Newton. And how far is it? It is 0.12 meters from the pivot, okay? And then, on the other hand, we have this force on the chain. So this is the pivot, yeah? So that's how far it is. Now, if this force here were to turn, so this is clockwise. So therefore, F is going to be here, okay? And how far is it from the pivot? We know it is 0.2 meters from the pivot. Here we go. And all we have to do is bring this here. So anti-clockwise, so total anti-clockwise moment equal to total clockwise moment. So anti-clockwise moment is F times D is equal to F times D. So therefore this is 1.5 times 0.12 is equal to F, which we're looking for, times 2. Okay, so therefore we're going to have 1.5 times 0.12 divided by 0.2 equal to F, and F is equal to 0.9. Here we go. Now for those of you who got this wrong, make sure that you have a diagram here to help you out. So this is the diagram which I've done to help us out, and then you've listened to the instructions, you know exactly which way is the anti-clockwise, which one is in clockwise, and then fully working out. Okay, good. Now this is a nice question. So use the gear to slow down rotation. So slow down rotation. Now the gear that's powered is 20 teeth. Okay, so we have a 20 teeth gear. 20. Now the question tells you that they want to slow down the rotation, the speed of rotation. Now, which gear size can rotate slower? So this is a big gear. So therefore, we have a small gear connected to a big gear. Now we know the teeth number of the small gear, which is 200, and the 200 one always turns faster. So the 200 is turning 300 times faster. Okay, it drives on the wave another gears which turn 60 times per second. So 60 times is slower. So therefore it has to be a big one. So therefore the number of teeth must be higher. Okay. So what we need to do first is we need to do our ratio. So teeth ratio. So we got 20 dot dot x. We don't know what x is. And what we have is we have the speed. Okay, so the speed ratio or rotation ratio. So we know that the small one turns 300 times per second, and the big one turns this many times per second. Okay, so therefore what we can do is we can do the ratio with this one. So therefore this is 1, therefore this is 5. Okay, so what we have now is we know that the small one turns 5 times faster compared to the first one. So therefore the large gear equal to 5 times less. Okay, so it's going to rotate 5 times less, isn't it? Okay, now we know that the second gear, okay, let me just delete this. Okay, so 5 times less, yeah? Now we know the second gear is going to rotate 5 times less, so therefore 6 times. Therefore, we also know, so if the second gear rotates slower, so rotate slower, so this means it's going to have it's going to be a large gear. So therefore it's going to have more teeth. How many more teeth it's going to have? So therefore it's going to have 5 times more teeth. So therefore it's going to be 20 times 5, which is going to 100 teeth. Here we go. Okay, so therefore it's going to have 100 teeth. Again, for those of you who got this wrong, make sure that you have the full working out there for your 2 marks. Okay, so therefore what we have is we have a small gear, okay, which is rotating 300 times, and the big one is rotating only 6 times, which is 5 times less, so therefore you need to have 100 teeth. Okay, now you guys should know this by now. Okay, let me just do this here. So here, this one, I need to see the word oscillations. You need to see the word oscillations again. Okay, so oscillations are so this one here, they are parallel or perpendicular to direction of energy transfer. Okay, now you can see that most of the sentence is being repeated, but we need to get the full marks for that. Okay, good. Now amplitude is pretty much the height of the wave, so from here to here, so this is the amplitude. Now how I know, so this is 2, 4, 6, so therefore by default the next one will be 8, therefore this is 8. Now wavelength is from one peak to the next peak, so this is wavelength. Okay, alright, again, so look carefully, it's from here to here. Okay, so that's 5. Alright, so 5, half of 5, and half of there. How much is it going to be? So this is half of 5, so this is 2.5, and this is half, so this is going to be 12.5. So therefore, the wavelength is going to be 12.5, take away 2.5, and this is 10 centimeters. Okay, here we go. Good. Now use information to work out the frequency. Now frequency is number of waves per second. Now how many waves do we have? Alright, let's take a look at number of waves per second. Okay. Alright. Now there are 2 ways you can do this. I'll show you this one, number of waves per second, and then I'll show you the other one, which is 1 over time. Now number of waves per second. How many waves do we have? So complete wave we got 1. So this is 1 wave. This is 2. We have 2 waves, 2 complete waves, number of oscillation to 2 complete waves, passing a point per seconds. Okay, now we can just do 2. Okay, so this will also work. So 2 waves, how many seconds does it take? It goes from 5 seconds all the way to 45 seconds. Okay, so it took 40 seconds to go through. Therefore, this is 0.05 hertz. Okay, so look, there's 2 complete waves. I've done it with complete waves. You can actually do it with other waves. So let's have a look. So 1, 2, there's 2, there's 2.5. Okay, 2.5. So that's half of the wave, and then this is a quarter of the wave. Okay, so you can also do the same thing with 2 plus half plus a quarter. This will give you 2.75. And how long it took? 55. Let's take a look whether this works. Yeah, and this also works. So 0.05 Okay. Now, for those of you who counted the whole wave, then there we have two. So we got, you can see the two complete wave. You got a half here, and then you have a quarter of the wave here, and the whole time it took is 55 seconds. You can do it this way, or alright. And another way you can do it is for those of you who done f is equal to 1 over time period. So 1 is one wave, so therefore one wave is this from here to here. So this is one wave, and the wave took, so from 5 to 25, that's 20 seconds, and then this will give you the same answer there. So three ways in which you can do that. Okay, so if you counted two complete waves and how long it took for those two complete waves to go, so that's 40 seconds. If you counted the whole wave, that's 2.75 waves, and the whole wave took 55 seconds. You give the same answer. And if you did 1 over capital T, that is one wave over 20 seconds, same answer there. Okay, so three ways. Now, wave frequency, wave speed is f times lambda. Okay, now frequency we know, which is 0.05 from the question that is given to us. Now, the waves are not the same, but the question is telling us use the information. So we're just going to follow the questions, yeah? I'm just going to follow the questions. So find the frequency from B, so we'll find frequency, and wavelength from part B, wavelength is 10, so 10 there. Okay, and then the answer is 0.5 meters per second, and that is my speed. If you've got this wrong, fix it. Okay, echolocation. So ultrasound are pretty much ultrasound. There are sound waves with frequency above 20,000 hertz. Okay. Now this one, the question tells us that the wave come back, so therefore this is echo. So therefore distance is equal to speed times time divided by 2. The speed we know 1500 times time. Time is 0.1 divided by 2, and this will give me 75 meters. There, done. Okay. Now, which is an example of longitudinal waves? So radio wave is transverse, light is transverse, water is transverse, so therefore sound is the one. Okay, now here, and it's still working out, so frequency is number of waves per second, so therefore 600 waves per minute. So 1 minute, how many seconds 1 minute? Here we go, and this is 10, the answer is 10. Okay, so are they transverse? No. Can they travel? They cannot travel in vacuum. Good. Remember, so only 2. So this is the one. Okay. Right, now the average. So therefore, average. So acceleration is equal to average. We need to read this one here. So this value here. This value here, which is 26. So this is 26. 26 take away 0 over 6, and this will give me this much. Okay, if you got this right, if you got this wrong, working out. Okay, now let's take a look. Power is equal to energy over time. Now energy, what is energy? Now what's happening is we are going up, so we're going up, so we're going from here to there, so therefore this is GPE. So this is GPE over time. So GPE is mgh over time. So m we know 65, g we know is 10, h we know is 5. So 5 climbing up 5, and time is 65. Okay, and then we should get, alright, we should get 500 watts. If you got this wrong, full working out. Okay, now the sun and the earth, how does the sun energy get to us? So this is a wave, isn't it? So conduction, there's no solid in space. Convection, there's no fluid in space. Radiation is the only one. Here you go. Alright, so make sure that you list down these things. Okay, so here, what you need to see the largest difference in temperature. Okay, so here, the difference is 0. Here the difference is 10. Here the difference is 20. Here the difference is 30. So therefore it is D. Okay. Again, make sure that everything's fixed up. Okay. To make sure that in the future you get full marks. Peace out.